Okay, so today we're going to take a look at permutations. Last day we just looked at the fundamental counting principle. So to get you thinking about what a permutation is, we're going to start with a couple examples. So the first one, you have a family of 7 children and you need to assign 5 jobs. So how many ways could we do this? Well, if you think about it like fundamental counting principle, what we're trying to count is how to hand out 5 jobs. So 1, 2, 3, 4, 5 choices we have to make. The first job, there'd be 7 children there. Then there'd be 6 possible children, 5, 4, 3, and then the lucky 2 who don't have to do any of the jobs. So we could figure out how many ways we could assign those jobs. So there would be 2,520 ways of assigning 7 children 5 jobs. Okay, good news. You get your air miles statement. You find out you have enough points to travel to any 5 capital cities within the provinces. So how many different routes could we travel on? Okay, well, assuming that we have 10 provinces still, 3, 4, we have 5 of them that we'll get to choose. So for the first choice, any of those 10, do a better job there, any of the 10 provinces, we could pick any capital. Then there's only 9 capital cities left. 8, 7, and 6. So that leaves us with a mere 30,240 different possible routes that we could take. So let's talk about what we're actually studying today. We're going to take a look at this thing called a permutation. So a permutation is when we have a group of objects and we want to place them in less places than we have. So for example, n must always be greater than or possibly equal to r, whereas last day we were looking at when we were using all of the things that we had. Okay, so it's possible to find this on your TI-83. This is the key that you're looking to use, and here's the steps that you use to find it. And just to illustrate here, there are 7 children, but I'm only assigning 5 jobs. So this would be a permutation of 7p5 in your calculator, or a permutation of 5 objects from the 7. Again, this would be 10 capital cities, and we get to choose 5 of them, so that would be the way we could illustrate this as a permutation. So just to make sure you can do this in your TI-83, why don't you pause it here and enter in 7p3 just to verify that we get the same answer. Okay, oh sorry, and again, you can hit your math key, and you're going to shift over to the right until you go to the probability menu, and then you'll see this key here, NPR. So in my screen, what it actually looks like is 7NPR3, and it's 210. Okay, so we can take a look at this. Before we go any further, just one thing, I've mentioned it here, but I really should highlight this for us. No object can be repeated, and the order does matter. So when we're talking about the situation of a permutation, we cannot reuse anything, and the order matters. Okay. So, for example, in the first one, if we want to make 3-letter permutations, you know, we would think of something like, I don't know, net is different than 10, right? Now, it just so happens that those end up being real English words, but I mean, we're also interested in this case in things like, you know, T and E, any arrangement of those objects. So we're not repeating them, and the order is significant. It does matter, so this is a permutation. There's 1, 2, 3, 4, 5, 6, 7, 8 letters. So this will be 8, and we're going to do a permutation with 3. And that means we'll end up with 336 possible permutations. So the next one also illustrates the same point. If we have a race with 15 people participating, and we want to know how many ways can we have the top 10 finishers. Well, the order obviously matters here, right? Because you want to be first, and then if not, you want to be second, and you know, on the way down. So the order matters to us, which is good because that's talking about a permutation. And you can't repeat, right? Once you cross that finish line, that's it. It can't be reused. So there are 15 objects. This is a permutation of 10 of them. And this seems like a very simple problem, although there are quite a few. I'm going to round it to the next decimal place here. Okay, so there are a lot of ways for this race to finish. So when we talk about counting, some very simple problems end up having a huge answers. And if you do have time, you should go and check out the traveling salesman problem. It's a classic problem which seems easy on the surface, but because of this idea of counting, it gets very, very difficult with even a small number of cities in the problem. I guess I should also mention that there's $1 million prize if you figure it out. So that's called the traveling salesman problem, and it's the Clay Math Institute that will give you $1 million for solving it. Anyway, so how many ways can a license plate be created with 3 letters and 3 numbers? Repetition is not allowed, okay? And it doesn't say so, but obviously the order matters in a license plate. The order will dictate whether the license plates are the same. For example, A, B, C, 1, 2, 3 is not the same as B, C, A, 3, 2, 1. Okay, so both of those things check out, no repetition, and order matters. So if we wanted to do this, we can do it a couple ways. First, we could talk about it with the fundamental counting principle like last day. So 3 letters, 26 to choose, 25, 24. Or it could be 3 numbers, 10 digits, 9 digits, 8 digits. We could also do this though if we recognize it as a permutation. So if we did it as a permutation, it would be 26 letters, and we'll do a permutation with 3 times 10 digits, do a permutation for 3. So both of these will give us the same answer, which is 11,232,000, so 11,232,000. Okay, so another thing that we're going to have to recognize here now that we're getting to use factorials a bit more is, how can we write something as a factorial? So I'll do the first one with you. For example, in this one, it almost looks like a factorial, but this is what I'm missing. So I can't just add it without changing this. What I have to do is make a fraction. So this whole fraction here, if I look at what I just added, this equals 1 because its top and bottom are identical. But what I've done is now I can see that the top, so the top of the fraction is 7 factorial. So 7 factorial, and then the bottom is 4 factorial. Okay. And if we wanted to then go a step further and write it as a permutation, I have to figure out 7 minus what will get me this answer. So to get back to 4, it would be 7 minus 3. That tells me this would be 7p3. So why don't you pause it here and try and see if you can figure out how to do the next one in permutation and factorial notation. Okay, so hopefully you've had a chance here. Again, if I was to do this all the way down, 10, 9, and it would go all the way down to 2, 1, and we want to do the same thing on the bottom. All the way down to 1. So then I can see I'd have 15 factorial on the top and 11 factorial on the bottom. And if I wanted to do this as a permutation, then I'm trying to figure out 15 minus what is going to be equal to 11. So that'd be 15 minus 4. So that tells me this would be 15. We're going to do a permutation with 4 of those items. Sometimes you may also come across a question in the non-calculator portion of the exams where you're trying to do this evaluation without a calculator. So for example here, if I was to think about this definition, this is 9, 8, 7, 6, 5, 4, 3, 2, 1. And I mean, it's possible to do this with multiplication, but it's going to take a long time. So if we just take a look at the expansion, then what you can see is if I count from the largest, which is here, down to the smallest, so this is my smallest at 7, then what it's going to do is it's going to chop off all of that because it's just equal to 1. So that means it simplifies a lot. It's just going to be 9 times 8, which hopefully you can do without a calculator. That's 72. Okay, so same thing happens in the second one. Why don't you try and tidy it up yourself? Just pause it here and then I will verify it with you. Okay, so again, if I count, this is the largest value, and I want to think about what I'm going to count down to. It'd be nice to get rid of the 5 factorial because that's such a large number. Okay, so if I was to do that, it would be like 7 times 6, and what's left over is 5 factorial. And the nice thing is then these will go away, and what I'll have is 7 times 6 over 2 times 1, and again, I hope you can do that without the aid of a calculator. It'd just be 21. So along a similar idea here, we're going to have to try simplifying an expression. Sometimes instead of having numbers, we're simplifying it algebraically. So some of those previous warm-ups were to try to get you in the mode of using these factorials. So now it's not numbers, there's a bunch of n's in our question. So what I'm going to do is I'm going to think about it the same way. I have to first think of taking the largest factorial and counting down to the smallest. So on the top here, this is still the largest because this one is n minus 2, or 2 less. So I could rewrite this. It would be n times n minus 1, and then I'd have all the numbers from n minus 2 down to 1. So this does simplify a lot more. These pieces would cancel out, and I'd have n times n minus 1, or n squared minus n. So that way I don't need all the factorial notations. It simplifies down to just those n squared minus n terms. Okay, so these next two, I'd like to have a bit more room, so I'm going to do them on a different slide. You may have enough room, but I find when I'm explaining things it's better to have more space. So the one that I'm going to solve first is n permutation of 12 objects. Permutation of 2 objects equals to 12. So the formula again for permutation is that we have npr equals n factorial over n minus r factorial. And it is a formula that's provided on your exam sheet, so don't worry about memorizing it. We will then take a look at how we can substitute this. This would say n factorial over n minus 2 factorial must be equal to 12. So just like before, we want to try to simplify the top and bottom of this. So I'm going to count down from the largest to the smallest. And that gives me something simplified that looks like this. So I have a quadratic equation now. And by now you should be used to solving these. Been doing it for quite a while, so I'm just going to whip through the factoring of it. And I get a couple possible answers. So I get n could be 4 or negative 3. But much like when we talked about logarithms, we have to take a look at our answers and see if they make sense. So negative 3, we want to reject that. It doesn't make sense to count a negative number of things, so we're going to remove it. We would do the same thing if we ended up with a fraction like a half. For our counting numbers in this course, we're just going to deal with the positive integers, okay? Or the natural numbers, I guess. Let's take a look here. N was equal to 4. I'm going to have you try solving this one. So you go ahead and pause the video and see if you can solve this one, and we'll verify again together. Okay, so for the next one, we have, switch back to red, we have a permutation on 2 objects again, equals to 42. So it probably won't surprise many of you that we're going to go to the same, almost identical set of tasks. Now the answer is going to be different because it's a different number that's involved, but I'll still work it out for you. And that means these cancel out. and I get n times n minus 1 is 42. So n squared minus n minus 42 is 0. So factoring this, I get a couple possible answers. And again, if we look at which ones make sense, negative 6 won't. So we have just the one answer here of n equals 7. Okay. So we're going to go back to doing some more word style problems instead of having these algebraic ones. And the next set of topics we're going to take a look at, I call them Mississippi questions. So you may hear them deemed a different way, but you'll understand why I call it that very shortly. So to illustrate this concept, what I'm going to do is I'm going to show you basically what we're looking at is where letters are repeated. So it's kind of like a permutation where some things are repeated. Okay? So for example, in the word, we'll try a simple one first. We'll try mom. So M-O. And I'm going to draw the other M a different color on purpose, and you'll see why that is shortly. And then again, if I did this, I could go, let's see here, M-O. Actually, they're not incorrect. I'm just going to move them so I have a little bit more room. I'll show you what I mean here. I'm just going to put them a little higher up on my page. So if I have M-O-M, and I have, I could do O-M-M, and another one I could do, let's see here, is M-M-O. Now, some of you might be saying that's all the words we can get because there is repetition. You know, we don't recognize these as different words because if I was to just do the permutation on them, that would mean this black M would have a chance of being first. And again, in this example, so it would be O, and then it would switch places, as well as here, where it would be switching places one more time. So all I've done is the difference between the top and the bottom is the number of ways I can rearrange the M. Right, because there's two M's in mom. That's why I have two identical rows. All I've done is I've switched from here to here, switched from here to here. Same thing in every one of these examples. I've just switched them. So it's easy for me to figure out that way. That's two things that I could rearrange, so there's 2 factorial. So before we go ahead and we say, well, in the letter mom, there are 3 items, so there are 3 factorial arrangements, we have to be a little more clear. We have to say there's 3 factorial arrangements. That's all 6 that are here. But we have to remove or divide out the repetitions, the 2 factorial for the 2 M's. So that's how I get 6 divided by 2, which is 3, and that was the original set of words here. Okay, just those 3. Now, obviously, for a word like mom, it's simple, but for a word like Mississippi, it gets a lot more challenging unless we have the strategy. So this is where the style of question gets its name for me. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 items. So there would be 11 factorial ways we could arrange those letters. Then within all those arrangements, all I've done is I've rearranged all the I's, I've rearranged all the S's, and I've rearranged all the P's. So I don't want all those duplicates. I want to remove the 4 factorial that represent the I's. There are 4 I's. The 4 factorial that represent the S's. And the 2 factorial that represent the P's. So in fact, if I rearrange the letters in Mississippi, there would be 34,650 unique number combinations. Okay, so if we're dealing with a permutation that has repetition in it, and each of these items has a particular number of repetitions, then this would be the formula where I only need to deal with the repetitions that happen. Okay, now it's not always a word. You have to be able to recognize these Mississippi questions can take on a different style. So for example, a football team plays a 10-game schedule. How many ways can the schedule end with 5 wins, 3 losses, and 2 ties? So what we're saying here is we have to figure out what technique we're going to use when we count it. For example, if I try and list a couple of these, sometimes that can be helpful in figuring out what technique makes sense. So let's just say that they start out really great and they have all these wins, and then they start to slip. They got 2 ties, and then they lose their last 3 games. That's one possible schedule. Another one, they could go win, tie, win, loss, win, loss, and win, loss. So they could kind of alternate like that. You can try more examples, but hopefully what you're seeing is this is just like rearranging. I have 5 W's, I have 2 T's, and I have 3 L's. Okay, so I have a total of 10 games, and the repetitions I get is there will be 5 factorial wins, there will be 2 ties, and 3 losses. So I want to remove those. So if this was the schedule, then let's find out how many games that they could play. Okay, so there's 2,520 possible, let's see here, I guess possible ways they finish their season. Okay. So similarly again, if you have a multiple choice test and the teacher was to tell you that there are 5 A's, 3 B's, 4 C's, and 8 D's, and that was what you're trying to fill out. With 20 of them, I'm not going to repeat them all, but it's going to be some repetition of the A's, the B's, the C's, and the D's. So it is a 20-question test, and I'm using the objects. Order matters, right? If you get the order wrong, you're not going to have a perfect mark on the test. So 5 A's, that could be rearranged, 3 B's, 4 C's, and 8 D's. So, that may sound like a nice hint, and I'm sure it is helpful for some people to hear that and double check their work. But, it really doesn't help you out in, reducing the number of possible answer keys. It's still going to be pretty hard to guess your way through that test. But again, I guess it is helpful to double check your work. Okay, so if we take a look again, if we want to get from point A, which is here, to point B, which is there, and we want to figure out how many possible paths are there. There's one in which I could go like this. I could do another. Maybe I go like this. But how will we come up with a clever way of counting them all without having to figure out, what we're actually doing here? Well, I can show you a little bit of this. If we're moving east and south, that means one possible thing, if I look at it, I can only move 2 souths, and I have to move 1, 2, 3, 4, 5 easts. Okay, so that makes for a total of 7 moves. So if I wanted to figure out how I could count this using our techniques, there will be 7 factorial arrangements, but 2 of those duplicates are S's, and the other 5 are E's for south and east. So we can count this quite easily without having to resort to just, drawing the paths and counting them all up. So for this particular one, there's 21 possible paths. So again, if you're getting the hang of Mississippi, and I guess I've given you a pretty huge hint here, but try doing the second one and see what you come up with. And I'll probably want to pause it here. Okay, so in this question, we end up with 4 south, and 1, 2, 3, 4, 5, 6 that I move east. So there's a total of 10 moves, 4 duplicates and 6 duplicates. So in this possible configuration, there's 210 paths. Okay, so the last thing we'll take a look at is what if there's restrictions on these Mississippi questions. For example, whoops, too far. For example, if we're taking a look at the word assessment, okay, that would be a straightforward Mississippi question. But say we have some restrictions, like the first one I'm giving you here is the first letter must be an A. So the way I'm going to approach this problem is, as my suggestion up here says, is we're just going to ignore the fact that there's a Mississippi question happening, and we'll deal with that later. So let's just say it was any old counting problem we were doing. We'd say, well, if A must be first, there's one possible way to put an A first. Then there's 1, 2, 3, 4, 5, 6, 7, 8, 9 letters left. So there would be 9 factorial for the remaining letters. Okay. Now, in addition, though, as I've said, we've got all these S's that are going to be repeated, and we've also got these E's that are going to be repeated. So if I want to remove those duplicates, then it's simply the problem I just solved, but then I remove the duplicates. So it'd be 9 factorial divided by 4 factorial times 2 factorial. Okay, so in that way, I've been able to count the problem like we would have before and remove my duplicates after. Okay, so let's see what we end up with here. So that's 7,560 possible arrangements if an S must be first. Okay, so now what we're going to do is, what if the S's must be together? So again, ignore that this is going to have some duplicates in it. Let's just count the problem in front of us. What if S's must be together? Okay, if S's are together, then I'm not going to think of this problem as having 10 letters anymore. Then I'm going to think of this having, let's see here, 1, 2, 3, 4, 5, 6. So think of this as having 7 letters, where one of those letters is all the S's sticking together. Okay. So that means there'd be 7 factorial ways of arranging those 7 objects, but also internally I'd be able to rearrange those 4 objects inside here. So those 4 could be rearranged. So that's how we would do it. And if this was a Mississippi question, right, because now we have to get rid of those duplicates when we also have repeated S's and repeated E's, I divide by 4 factorial for the S's and 2 factorial for the E's. So one nice thing is those will disappear, and let's see what we end up with. Okay, so we end up with 2,520 possible combinations if the S's must stay together. All right, so that concludes our lesson for permutations.